Hello and welcome back to the Biochemistry for Health Sciences channel. In the previous video, we briefly discussed the hyperbolic and sigmoidal curves. In today's video, we shall have a closer look at these two types of curves. The hyperbolic curve, in case of enzymes, where we plot the velocity of the reaction against the substrate concentration, this hyperbolic curve is also called the Michaelis-Menten curve. So let's analyze the Michaelis-Menten curve. Keep in mind the way enzymes work. The enzyme basically binds the substrate. You get an enzyme-substrate complex form. The substrate is converted to the product. The enzyme is free, and the enzyme can go back and catalyze another reaction. So let's look at this Michaelis-Menten curve a little bit more closer. First, let's look at low substrate concentration. When the substrate concentration is very low, we see that most of the enzyme is in the free form, the E form, not the ES form. And during this time, you can see the beginning part here it's linear. That means the velocity of the reaction is increasing in proportion or linearly with the substrate concentration. So that's the first part of the curve where the substrate concentration is very low. In the second part of the curve, as more and more substrate combines with the enzyme, more and more of the enzyme is now in the ES, enzyme substrate complex form. Now you will see that there's no more a straight line. You can see it is curving. So the velocity is no longer increases in proportion to the substrate concentration. So we lose the linear relationship between velocity and substrate concentration somewhere here in the later part of the curve. Now at very high substrate concentration, we now see that almost all of the enzyme is in the ES complex form. So there's hardly any enzyme in the E form. All of it is in the ES form. And at this stage, increasing the substrate concentration, even if we increase the substrate concentration, the velocity is not changing much at all. It's very, very close to maximum. We say that the enzyme is saturated with the substrate and the maximum velocity has been reached. So at very high substrate concentrations, we have saturation of the enzyme. So to summarize, at one extreme, we have a linear relationship between the velocity and the substrate concentration, and at the other extreme, the velocity does not depend anymore on the substrate concentration. We can also analyze the Michaelis-Menten curve using the Michaelis-Menten equation. So this is the Michaelis-Menten equation. The velocity, the initial velocity of the reaction depends on Vmax multiplied by substrate concentration divided by Km plus the substrate concentration. So when the substrate concentration is very low, then Km, if the substrate concentration is very, very small compared to Km, so in other words, Km is much, much larger than substrate concentration. And if that's the case, then adding Km to substrate concentration is more or less equal to Km. For example, if Km was 1000, and substrate concentration was 1, that would give us 1001. which is very close to just Km itself of 1000. So we can basically ignore this substrate concentration in the denominator and we just get our Km. So in this case, the velocity is directly proportional to the substrate concentration. Okay, so when the velocity is directly proportional to the substrate concentration, this is called a first order reaction. So at low substrate concentration, we have a first order reaction. What happens if the substrate concentration is exactly equal to Km? Well, then we simply substitute, instead of Km in this equation, we put in S. So instead of Km here, we put in S. And if we do that, we get velocity equals Vmax times S divided by 2S. And this comes out to be, so S and S cancel. So it's basically Vmax over 2, which is 0.5 Vmax. Okay, so when substrate concentration is equal to Km, the velocity is exactly 0.5 Vmax or 50% Vmax. And this is the definition of Km. Km is that substrate concentration at which the velocity is 50% Vmax. Okay, so Km is a substrate concentration at which the velocity is 0.5 or 50% Vmax. So that's the definition of Km that we've just proven mathematically. Now let's look at the other extreme. What if the substrate concentration is very high? So substrate concentration is much higher than this Km value. So S is much, much greater than Km. So in this case, we can ignore Km. We can ignore Km. Okay, so V equals Vmax S over S, and that S and S will cancel. We get V equals Vmax. So basically, when the substrate concentration is very high, the velocity is independent of substrate concentration. We call this a zero-order reaction. Okay, in fact, this is the condition that we use to measure the amount of enzyme in a blood sample. Okay, because the amount of enzyme in a blood sample is proportional to its Vmax. So this is the condition. So we actually add saturating concentrations of substrate when we want to measure the amount of enzyme in a given sample, such as a blood sample or urine sample and so on. Okay, so that's a little bit more about the hyperbolic curve or the Michaelis-Menten curve. Now let's look at the sigmoidal curve. So here is the equation for the sigmoidal curve. In case of sigmoidal curve, the n is less than 1 or greater than 1, but it's not 1. If n was 1, then that equation would become the Michaelis-Menten equation for the hyperbolic curve. So when the substrate concentration is very low, the substrate is binding each enzyme molecule, and we see a gradual increase in velocity with an increase in substrate concentration, just as we saw with the hyperbolic curve. However, unlike the hyperbolic curve, these enzymes that show sigmoidal kinetics show a very interesting phenomenon when at a certain substrate concentration. So in this case, you can see when the substrate concentration reaches around 5 or so, the velocity suddenly shoots up real fast, with a slight increase in substrate concentration. So this is the dramatic difference, a major difference between the sigmoidal curve and the hyperbolic curve. Very slow increase at the beginning, and suddenly the velocity shoots up. So in this example, as the first substrate molecule binds each of the enzyme molecules, the second substrate molecule and the third substrate molecule somehow binds easier to the enzyme molecule. So basically the enzyme is showing what we call as a positive cooperative effect, positive cooperativity. So the first enzyme molecule binds the usual way, but the second and subsequent enzyme molecules bind the enzyme easier, much faster. And that explains this sudden rise in velocity with a slight increase in substrate concentration. When the substrate concentration is very high, then we see a situation very similar to the hyperbolic curve, and that is the enzyme becomes saturated with the substrate and the maximum velocity, or Vmax, is reached. And once again, we do not see a relationship here between V and S. So velocity is independent of substrate concentration. So just to summarize, in case of the hyperbolic curve, we see a gradual increase of velocity with substrate concentration, and then which eventually plateaus into the Vmax, where the velocity is independent of the substrate concentration. So this is what we say saturated enzyme. The enzyme has become saturated and cannot work any faster. In case of the sigmoidal curve, once again we see a gradual increase and then a sudden dramatic increase, and finally reaching the plateau phase. And this is what gives the sigmoidal curve its S shape. So this figure shows you clearly how a hyperbolic curve where n equals 1, shown in the blue line here, slowly becomes a sigmoidal curve. And here you see examples of n going from 1 to 1.5, 3, and then 6. And you can see as the n increases, you can see the S-shaped characteristic. The S shape becomes more prominent. Okay, so that's a little bit more about the sigmoidal curve compared to the hyperbolic or Michaelis-Menten curve. So to understand these curves, let's try to do a few problems. So the following data was obtained at pH 9 and 37 Celsius. Remember, very important, when we do experiments with enzymes, we must specify the temperature as well as the pH so that we can compare apples and apples, because others may do the experiment at a different pH and or at a different temperature. So this data was obtained at pH 937 Celsius, and the question is, what is the Vmax and what is the Km? So if you look at the data, you can see the substrate concentration increasing here. PNPP is the substrate for alkaline phosphatase. And you see the velocity of the reaction, the rate of product formation in this column. If you look carefully at the velocity, you can see that it goes up 1.2, 2.5, 3.1, 3.8, and then it goes to 5, and then it remains at 5. So it remains at 5. So clearly 5 is the maximum. So the Vmax is 5 millimolar per minute. Now, to find the Km, we simply, okay, if the Vmax is 5, then we take 50% of Vmax. We want 50% Vmax or 0.5 Vmax, and that should be 2.5, right? 50% of 5 is 2.5. So we look at 2.5 and we see 2.5 is right here. This is 2.5. Okay, so the velocity 2.5. Now we extrapolate it to the substrate concentration, and that comes out to be 2. So the Km, which is the velocity at 50% Vmax, is 2 millimolar. So Km is 2 millimolar. So just by inspection of this data, we can figure out, in this case, Vmax and Km. Okay, problem 2. What is the velocity V of an enzyme catalyzed reaction when the substrate concentration is 0.5 millimolar? The Vmax is given 52 millimolar per minute. Km is given as 0.6 millimolar. The pH has been identified and specified, as well as the temperature. So basically the question is, what is the velocity of the reaction if the substrate concentration is given and the Vmax and Km are given? So this is your Michaelis-Menten equation. Notice the units are the same, millimolar here, millimolar here. So we want to make sure the units are the same so that we can cancel them out. Then we substitute the Vmax, put in the Vmax, substrate concentration is 0.5 millimolar. You want to put the substrate concentration here, and then the Km is given as 0.6 millimolar. You want to put the Km here, and then you solve the equation, and the answer comes out to be about 24 millimolar per minute. So at 0.5 millimolar, the velocity of this, the initial velocity for this experiment, is about 24 millimolar per minute. Problem number 3. What is the relationship between Km and substrate concentration when a reaction catalyzed by an enzyme proceeds at 80% Vmax? 80% Vmax. So basically, a question is asking, what is the relationship between substrate concentration and Km? What's this relationship? When the reaction proceeds, so that means the reaction velocity is 80% of Vmax. Okay, so instead of 100% Vmax, it is only at 80% Vmax. Okay, so at 80% Vmax, what is the relationship between substrate concentration and Km? So here's the Michaelis-Menten equation once again. We can rearrange this equation, bring Vmax down here, so we get V over Vmax, and then we have equals to substrate concentration divided by Km plus S. So 80% Vmax means V divided by Vmax is 0.8, that's 80%. So this is basically our V divided by Vmax. That's 80%, 0.8. So we know this is 0.8. Now that's equal to S over Km plus S. We solve for this. 0.8 times Km plus S will give us S. Work this out, and you get the relationship where the substrate concentration is equal to 4 Km. So this means that when the substrate concentration is 4 times the Km, so if this was your Km and the substrate concentration was 4 times as high as the Km, then the velocity is 80% Vmax. Okay, so that's the relationship between substrate and Km when the velocity is 80% Vmax. Problem number 4, what is the velocity when the enzyme concentration is 0.020 micromolar, substrate concentration is 5 millimolar, kcat is 100 per second, and Km is 10 millimolar? So we saw in an earlier video kcat, the turnover number, is equal to Vmax divided by the concentration of enzyme ET. Or in other words, Vmax is equal to kcat times ET. So since we have this relationship, so instead of Vmax here, we can put in kcat times ET. That gives us the kcat times ET here instead of Vmax. So we have velocity is equal to kcat times ET times substrate concentration divided by Km plus S. So we have this formula, and now we plug in the numbers. So kcat is 100, so that's kcat 100 per second. Enzyme concentration is 0.020 micromolar, so this is your enzyme concentration. Substrate concentration is 5 millimolar, so that's your substrate concentration, 5 millimolar. Km is the same unit, 10 millimolar, so that's your Km, 10 millimolar. Now notice that we didn't have to change this unit because this 5 millimolar here, this millimolar here, and this millimolar cancels. Okay, so we have only this unit left, micromolar and second. So when we work this out, the velocity comes out to be 0.67 micromolar per second. Okay, hopefully this video will help you better appreciate the hyperbolic curve and the sigmoidal curve. We'll have more videos on enzyme kinetics in the near future. Until then, goodbye and have a wonderful day.